Hello, everyone. Good morning if you're in the US, and good afternoon if you are other places. It's my great pleasure to introduce Alin Bostan, who will speak about deciding the algebraic nature of D-finite power series. Thank you.
Okay, thank you very much. Thank you for the invitation. I'm very pleased and honored to speak at a Colgin seminar. So indeed, the talk will be about how to decide whether a D-finite power series is algebraic or transcendental. So let's go with stating the goals, giving some examples, and some motivation. So let me recall that a power series F, so I will look at power series in one variable, t, with rational coefficients. So such a power series F is called algebraic if it is a root of some polynomial equation, non-trivial polynomial equation with coefficients in Q. Otherwise, it is called transcendental. So that's a very basic class, important class of power series. It contains, of course, polynomials. It contains rational functions that can be expanded as formal power series, Taylor series. Moreover, more generally, rational powers of rational functions that can be expanded in the same ring. And then the set of algebraic power series is a ring, actually a field. Sums and products of algebraic power series stay algebraic. And we have many examples coming from combinatorics, for instance. If we let Cn denote the number of Dijk walks in n squared with length n, like here, then the generating function is very well known to be algebraic. And of course, I will restrict in this talk to power series with coefficients in Q, but this definition extends to more general classes series such as Laurent series with coefficients in Q, or even Pizzo series with coefficients in Q bar. So this is the first word in my title. The second one is D-finite power series. So such a power series F is this solution of some linear differential equation, like here, or the R. All the coefficients are rational functions or polynomials with coefficients in Q, and that's a very well studied class of power series. It's also called holonomic or differentially or differentiably finite. Here is the first page of a very famous paper by Stanley on exactly this class of power series from 1980. And here is the cover of a very recent book by Manuel Covers on precisely the same class. Okay, so some examples of D-finite power series. Of course, we have the exponential solution of f prime is equal to f, or the one even constant coefficients. We have the log solution of linear differential equation over the 2 with polynomial coefficients of degree 1. Any rational power of a rational function is solution of such an equation over the 1. And it's a very well known and important fact that any algebraic power series is D-finite. So the first class is included in the second one, and that's usually attributed to Abel. Call it Abel's theorem. There are other, so for instance, trigonometric functions that are D-finite, such the arctangent, but we should keep in mind that not all trigonometric functions are D-finite. For instance, the tangent is not. And the set of D-finite power series is a ring. It's not a field anymore, but it's a ring. So some end products of D-finite functions are definite. There is a very simple but important property, which is that a power series is sum of a and d to the n is D-finite if and only if the coefficient sequence a is p-finite. So that means that this sequence satisfies a linear recurrence with polynomial coefficients in the index n. And we'll keep this in mind. Okay, so then our main question today is the following one: how to decide if a D-finite power series is algebraic. So we know from Abel's theorem that algebraic series are D-finite. The converse is not true. And the question is given D-finite power series to detect, to decide, to prove that it is either algebraic or transcendental. So since I'm formulating this question in let's say, algorithmic terms, I should specify the data structure. So when I say given a D-finite power series, well, such a thing is a priori infinite. It contains infinitely many coefficients, but it can be specified by this data structure, which is finite, the linear differential equation, and sufficiently many initial terms. So this is our input, and the output is a Boolean, either 1 if it's algebraic, or 0 if it is transcendental. Example, take this power series that starts like this, 1 plus 3t plus blah, blah, such that it is a solution, actually the unique solution, power series solution of this linear differential equation of 3 with polynomial coefficients. So the question is, what is its nature? Equivalently, since we have this duality between correspondence between having a D-finite power series or having a P-finite sequence of coefficients, our equivalent goal is given a P-finite sequence of rational numbers and by a linear recurrence with polynomial coefficients and sufficiently many initial terms, the question is to determine the algebraicity or the transcendence of its generating function. So the previous example becomes, take the sequence defined by these 4 terms, initial terms, and by this linear recurrence with polynomial coefficients. The question is it algebraic or is it transcendental? So in this particular case, yeah, I'm saying that actually this question of algebraicity and also of integrality or almost integrality of coefficients are related, as we'll see soon. In this example, we can prove something that is by no means obvious on the recurrence, that all the terms of the sequence are integer numbers. This is not obvious at all because of, you see, when we unroll this recurrence, we divide by this polynomial. So this a priori in this is denominators. But in this example, this is not the case. So integrality and algebraicity are related questions, but actually deciding integrality is harder, as maybe we can discuss at the very end. There are many motivations to look at this problem. Okay, first of all, it's very fundamental, very beautiful, and also it has it appears in many contexts. For instance, in mathematics, in number theory, when you want to prove that some number in transcendence theory, that some number is transcendental, then usually a first step towards this is to prove that some power series attached to the number is transcendental. Of course, in combinatorics, we have many generating functions, and knowing whether a generating function is algebraic may reveal some structural properties, or, for instance, recursive underlying, maybe hidden structures. Also, in computer science, the question is, theoretical computer science, is it easier to manipulate, to evaluate, to manipulate in any sense? Are algebraic power series easier to manipulate than other ones for the general D-finite functions? Okay, so the central problem in what I will discuss is the following thing. So I will call it Stanley's problem because it arises in his paper from 1980. And at the very end, he states several open problems. And one of them, probably the last one, still unsolved before this talk, let's say, is design an algorithm suitable for computer implementations that decides if, given a D-finite power series by a linear differential equation, as usual, with polynomial coefficients and initial conditions, decide if it is algebraic or not. So in order to be sure that we all understand precisely what this means exactly, imagine that you are given this power series. So, okay, we recognize the log of 1 minus t, but the algorithm will just take as input a finite amount of data, notably a linear differential equation here over the 2 with polynomial coefficients, represented here by a linear differential operator with polynomial coefficients, together with 2 initial conditions. And this data is sufficient to represent our object. So from this, the algorithm should recognize that f is transcendental. Recognize means here prove. Yeah, one more example. So the same algorithm should also be able to recognize the algebraicity of G such that, you see, the same differential equation holds, but I swapped the initial conditions. So this should also ring a bell in the sense that this property of being algebraic or transcendental does not uniquely depend on the linear differential equation. It very much depends on the initial conditions. Okay, so just a notation that I will anyway recall later on is the following one. Assume that you are given f, a D-finite power series. Then this notation L index f min will represent the least order, the minimal order, monic linear differential operator that cancels our D-finite power series f. It's a kind of, it's a differential analog of the minimal polynomial of an algebraic power series. Except that it's not a polynomial anymore. Well, it's a skew polynomial. It's a linear differential operator. In our problems, it's important to remember that this minimal thing is not known a priori. Only some multiple, right multiple of it is given as input. And one of the difficulties in these problems in this area is the fact that contrary to the polynomial case, the minimal, so the minimal polynomial of an algebraic power series is of course irreducible, but in this differential setting, this is not always the case. For instance, even in one of the simplest cases for the log of 1 minus t, the equation that I displayed earlier, its minimal operator is already reducible. There are some other related problems. So this is the one that I will mostly focus on, Steinleit's problem. There are older problems. For instance, Fuchs's problem is the one that asks to decide if given such a linear differential equation with polynomial coefficients, all solutions of it are algebraic. While Steinleit's problem speaks about a given solution. There is also Liouville's problem, a problem that I call Liouville's problem, which is to decide if given such a differential equation, it has at least one algebraic solution. Well, these problems are all equivalent if the input L is known to be reducible, but as we just saw, it's not always the case that our input will be irreducible. And so today I will talk about this, how to solve these 3 problems for a priori, arbitrary input. Don't hesitate to interrupt if something is not clear or if you have any question. So I'll start with some basic starting remarks and a bit of history of context and things that are already known, notably transcendence criteria and the one very important case, which is a hypergeometry case. So starting remarks. Well, first, something that concerns the data structure is the following very basic observation. Take this an integer n, capital N, assumed to be, think of it as being large, hence this is why I put it in capital. So f is now this the nth root of 1 minus t. That's this power series. As a, the minimal polynomial, of course, this one, y to the n minus 1 minus x, has a large degree, namely n, while there is a very simple linear differential equation that this f satisfies. It has order 1 and coefficients of degree 1. So in other terms, the minimal polynomial may have arbitrarily large size degrees with respect to the size or the degree of the differential equation. So the differential equation may be small, but in case where f is algebraic, its minimal polynomial may be very large. And actually things, and this is, let's say, a very basic example. Moreover, and yeah, another starting remark is that there is no known characterization for coefficient sequences of algebraic power series, contrary to D-finite functions. So we saw that for D-finite power series, the coefficients form a P-finite sequence. And actually, there is a much smaller class, the class of rational functions. And for this one, we also know a characterization. The coefficient sequences satisfy C-finite sequences, recurrences. So recurrences with constant coefficients, like for the Fibonacci numbers. There is also a class that I will come to a bit later, diagonals of rational functions. And there, conjecturally, by what's known to be Kristol's conjecture, the coefficients should be, D-finite, P-finite, sorry, almost integer, in a sense that I will define a bit later, but let's think of really integers or almost integers in a naive sense. And these sequences have a nice growth, geometric growth. And the last remark is that we are not at all the first ones to address such questions. This is a very fundamental question about knowing about algebraicity of solutions of linear differential equations. And there are many tools to study this. So that's a very quick history, let's say, in pointers, geometric tools, invariant theory tools, group theory, differential Galois theory, algebraic geometry, number theory. That's a really rich area. Now let me recall or let me spend a few moments on properties of algebraic power series. So I will classify them into three categories. So if F, that's my assumption, F sum of A and T to the N is algebraic, then we know by this theorem of Abel's that F is D-finite. Okay, that's something that I already told you. But there are also arithmetic and analytic properties. So among the arithmetic properties, I chose one very nice and important. It is the fact that F is almost has almost integral coefficients. Now I will define this notion. The proper word is that F is globally bounded, and this means that up to a rescaling, the coefficients become integers. So there always exists a C such that A and C to the N become integers for all N strictly positive. And that's a result, that's often attributed to Eisenstein. So Eisenstein indeed studied the question, and he discovered in his last paper, unfortunately he died when he was very young, that denominators of coefficients of algebraic power series only have finitely many prime divisors. And that was extended 2 years after by Heine. And as I mentioned, there are also analytic properties. So, in a sentence, the sequence of coefficients of an algebraic power series should have nice asymptotics. And by nice, what I mean is, for instance, a typical statement is the following one. Assume that an grows like a kappa times rho to the n and to the alpha. Then these numbers, kappa, rho, and alpha, should satisfy very strong constraints. For instance, alpha, the exponent of n, should be a rational number. And that is not a negative integer. While rho should be an algebraic number, and this kappa should satisfy this condition, which is that kappa times the gamma function applied to alpha plus 1, I recall the definition here, should be an algebraic number. That's really a strong condition. And all these things are nowadays called Flageolet's criterion, and that builds up and works by Puiseux and Darboux from the 19th century. So when think of these properties and take the reverse statements, in the sense that and there we will obtain transcendence criteria. For instance, if F is not D-finite, if we have a mean to prove that F is not D-finite, it will not be algebraic either. Example, the generating function of the partition numbers, since it has infinitely many singularities, it cannot be D-finite, hence it's not algebraic either. So that's the algebraic property. Then if F has infinitely many primes in the denominators, for instance, for this, the logarithm, the expansion of the logarithm of 1 minus log of 1 minus c, since the denominators contain infinitely many primes, then this implies by Eisenstein's criteria that F is transcendental. And the last one, which is usually the most useful in practice, for instance, we can apply it to what's called the Apéry power series. So this is a power series. These are numbers that were used by Apéry in his famous proof that zeta of 3 is not a rational number. So this sequence starts like this, 1, 5, 73, and so on. And here I'm considering the generating function. Well, what I'm saying is that using this Flageolet criterion, we can prove that it is transcendental in the following way, relying on two non-trivial, highly non-trivial results. One is the asymptotics of this Apéry sequence, given here. And notice that here the growth rho is actually an algebraic number, so we cannot deduce transcendence using the property on rho. Alpha is -3/2, so we cannot use this either. So we really need to go to the kappa, to the constant connection constant, and there when we write down the this condition that kappa times gamma of -3/2 plus 1. Then we obtain this number, which is known to be transcendental, but this is also a non-trivial result. And this is the reason why this proof, while perfectly valid, I will call it not a moral proof, because proving functional transcendence should be much easier than proving transcendence of numbers. And note that none of these criteria is an equivalence. And that's why we call them. Actually, we cannot use them as in order to systematically prove that a power series, D-finite power series, is algebraic or transcendental. And we'll have an example at some point. An example of a power series that is that has compatible asymptotics, that has finitely many primes in the denominators, and that is, by definition, we'll see D-finite. So none of these criteria can be applied in order to infer that it is transcendental. We'll see this a bit later. So let me, in order to finish this long introduction, mention that there is a case where we already have an algorithm that is, for which the silence question is known to be decidable. That's the hypergeometry case. So recall that algebraic power series lie inside the D-finite power series. And the hypergeometric sequence, or F is called hypergeometric if its coefficient sequence AN is hypergeometric, in the sense that AN satisfies a linear recurrence relation with over the 1 with polynomial coefficients, or in other terms, n plus 1 over AN is a rational function in N. And there are plenty examples, like the log we saw before, arcsine, properly scaled. Also, any rational power of 1 minus t is in this class. And more generally, all these three examples are generalized by what's called the Gauss hypergeometric function 2f1, with parameters alpha, beta, and gamma defined like this in terms of Pohama symbols, or rising factorials. And there is a larger class called the generalized hypergeometric functions, defined like this, with alpha parameters, p parameters on top, alpha 1, alpha p, and q parameters on the bottom. And there, the theorem, okay, that there are many authors, and I will not state it properly right now, but there is a theorem saying that for this class of the intersection of algebraic and hypergeometric on my picture, there is a full characterization. So this relies on, it was first proved by Schwarz by the end of the 19th century for two F1s. So he characterized the two F1s that are algebraic functions. And there were other approaches. So his approach was geometric. There were other approaches more with a more arithmetic flavor, Van Landau, Strinsberg, Herrera. And then there was a revival in the 1990s and 80s, sorry, 70s and 80s, and then the 90s by notably by Katz, Christol, Böckers, and Heckmann. And what I like very much is not only that there is a full characterization now of this class, but also we have an algorithm since 2024. And in the audience, we have at least one of the authors of this very beautiful, I highly recommend, Laurent Fernzi, and together with Sergei Sorokevich. Okay, so let me now come to the new results, and together with some examples. So our new results, together with Bruno Salvi and Michael Singer, that will be posted very soon on the archive, probably in a few days, are the following. So I picked three results. One is a decidability result. Namely, we have two theoretical, although impractical, algorithms for deciding the algebraicity or the algebraic or transcendental nature of a D-finite power series in K of t. We also have an incomplete but very practical transcendence test for D-finite power series. By incomplete, I mean that it is always correct when it returns transcendental, but it may fail when it returns algebraic. Although, modulo conjecture by Cristol and André, it is also always correct on differential equations that have some additional arithmetic structure. For instance, for all those that cancel diagonal of a multivariate rational function. And third and last thing, we have an efficient implementation. So I'll post the slides. You could click on this is transcendental. That's a link, hyperlink, and you will land on the web page of GFun, the package in Maple. But now this function is available in the latest version of GFun, so you can play with it in yourself. And okay, still open to design a transcendent test that is both complete and efficient. Let me use three examples in what follows. So the first one is this power series by Aperi that I already used before, and that I will illustrate the new approach on a bit later on. The second one is a geometry function coming from the world of enumeration of lattice walks in the quartal plane. So here the sequence counts walks in n squared of length n that start at the origin and anywhere in n squared, and that use precisely this type of steps. And the last one is a very similar one to this, except that now the constraint is that we should land on the horizontal axis, and that this is the step of allowed steps. This is the set of allowed steps, and you notice here that there are two ways of going to the direction of to the west. And the question is the common question is, what is the nature of these three power series? And well, the answer is our implementation proves that they are all transcendental. Yeah, this is something that I will illustrate on the first one. And if I have a few minutes more, maybe on the last one. Some timings. So now we are very happy that we have this implementation is transcendental, and we can play with it. We tested it on several classes examples. Here is one that is so it's a family. It's a family of functions that are defined like this. So this z should be a t with my previous notation. So these are well, that's a d-folded integral of this integrand that involves, you see, cosines, and d is the dimension. So for any d, we have such a function defined by this multivariate integral. By general theory, we know that this is the D-finite. We can compute, given a dimension, we can compute a differential operator. Here are the orders and the corresponding orders and degrees. And well, this column trans is displays the timings in seconds needed by our implementation is transcendental to prove that for these values of d, this function is transcendental. There is a last column that I will not comment too much. These problems are related to factoring differential operators. So one approach would be first, let's factor. And as you can see, it is more expensive to do so. And moreover, in many algorithms, this is one of the necessary steps that one should repeat, as I will recall in a second. So we should defactor the factor differential operators, and that's a costly operation. One of my messages is that we should, if possible, we should avoid factoring and replace it by something else that is called minimization, something that is hidden in this column. Okay, and one last example, I wanted to mention that there are these diagonals of multivariate power series. So for instance, two variables, you fill the quarter plane with coefficients of the Taylor expansion of a bivariate power series. Then you take the coefficients that lie on the diagonal, and this is the univariate power series. It's the diagonal of the initial one. The famous theorem by Polya says that this this thing is, if we start with a rational power series in two variables, then the result, the diagonal, is algebraic. So there is no question in that case. The proof is a very short here pictorial, but I will not comment on this. We see the diagonal as a residue, and the residue is algebraic if we have two variables. But then if we have more variables, this result is not true anymore, and there is a result by Crystal that says that diagonals of series of rational power series are not algebraic anymore in general, but they are still D-finite. So hence the question is well defined for us. Given a rational function in three and more or more variables, decide whether the diagonal is algebraic or not. And here I am displaying two examples where you have the impression that they are very similar. You see just a z added here, and this changes completely the nature of the diagonal. Even in more variables, diagonal may be algebraic, and most of the time it is transcendental, but the question is how to detect, to prove this. Okay, so let me, in the remaining part, mention a bit of technical things. So first, there is an algorithm by Singer from 1979 that solves Fuchs's problem. And this problem says, once again, that we want to decide, given a linear differential equation with polynomial coefficients over the R, we want to decide if all solutions are algebraic. It's not exactly our problem, but it's, of course, something in the same orbit. Well, in this algorithm by Michael Singer, the starting point is from differential Galois theory and group theory, namely a result, it relies on a result by Jourdan, 1878, that says that if indeed all solutions of this L are algebraic, then for some, there exists a solution, non-trivial solution, Y, such that its logarithmic derivative U is algebraic, and moreover, of algebraicity degree bounded in terms of, uniquely in terms of the order of the input equation. Something that is by no means true for Y itself. So we really need to go to logarithmic derivatives. Moreover, this thing, then that's not very difficult to see, satisfies a Riccati type equation of order one less. So the algorithm, at least in the irreducible case, can be summarized like here. We first build the Riccati equation over the R-1, and we decide if this equation has an algebraic solution of degree at most this bound. And if not, we stop. And if yes, then we need to continue, because we still need to decide whether this U algebraic that we found at step one really correspond to an algebraic Y. So we need to understand, to solve Abel's problem that asks, given an algebraic Q, to decide whether Y prime is equal to U times Y has an algebraic solution. And that's a very famous and famously difficult problem that was solved in the 70s by Risch and Baldassari and Wark. Well, actually, in the general case, Michael Singer proposed a generalization not only valid for irreducible operators, but on any input, and this requires as a first step factoring differential equations. So it's costly. And well, there is another generalization which is amounts to this goal to compute L-alg, which is the right factor of L, whose solution space is spanned by all algebraic solutions of L. Once you know L-alg, then you basically know everything about algebraic solutions of your input. This again requires factoring differential operators. Now let me just show you the connection to Stanley's initial problem. So the question is, once again, problem S, Stanley's problem, decide if a given D-finite power series is transcendental or algebraic. So there is a way to reduce what I said before, namely the generalization of Singer's 1979 algorithm to the computation of L-alg. We can apply this to solve Stanley's problem in a theoretical way. So first, we compute the first algorithm to solve problem S. First compute L-alg, and then decide, and that's not a difficult step, decide whether L-alg annihilates our given D-finite function f or not. The great benefit of this first algorithm is that it solves, in theory, all these three problems and shows in particular that algebraicity is decidable. So it solves partly, at least, Stanley's problem. But recall that Stanley insisted on the practical aspect, on the fact that he wanted that this algorithm is not only of theoretical interest. Now, it is really, this one is really impractical because first, step one involves many things, many impractical things in practical bounds, but also requires many difficult operations like factoring differential operators. This thing is effective, so we know it is decidable, and there are many algorithms to do to factor differential operators, but it is also known to be an extremely costly operation, at least in the worst case. So it was analyzed by Grigoriev in the 90s. And now let me, in the last minutes, tell you about a practical method that is based on what I called a minimization. And that's maybe the most important, and with the next one, the most important slide. So the main idea is the following one. Recall that LF-min denoted the least order monic differential operator that annihilates F. Then the key property that we prove is the following. If F is algebraic, then this LF-min has only algebraic solutions. And that's a sketch of the, actually it's it's the sketch of a proof in one line. And the idea is that, so let's call it M. Well, and take its alg. So M alg is a right factor of M. So it writes like this: M is equal to Q times M alg. Both assume that both M and M alg are harmonic. Then, since F is algebraic, F is not only a solution of M, but also of this factor M alg. But then by minimality, since we know that M is LF-min, so it's a minimal order operator that cancel F, then this implies that Q is equal to 1. So M is equal actually to M alg. So M has only algebraic solutions. That's a very sketchy proof of this property. The corollary that we are using in the algorithm is the following one. Now take the converse. Assume that LF-min has a logarithmic singularity, then necessarily F is transcendental, because otherwise, if F was algebraic, then LF-min would have only algebraic solutions, so there would be no logarithmic singularity. No logs may appear locally in the expansion of solutions. Well, this there are pros and cons. It avoids factorization of L, so that's something that is very costly, as you noticed in theory, but also in practice in my table with timings, but still it requires computing LF-min. But this is something that we know how to do efficiently since last year. Let me illustrate this approach on the same power series by Aperi, where I said that there is a proof using asymptotics, but that didn't seem moral to me because it used transcendence of pi, so of numbers. So let's prove that Aperi's power series is indeed transcendental. Well, there are a few steps. The first step is by a technique called creative telescoping that amounts, at least in this hypergeometry case, at least to Zagier and Zellberger in the 90s. You can easily, as of today, using a computer, deduce this recurrence over 2 with polynomial coefficients. Then you can convert this recurrence into a differential equation satisfied by the generating function of this sequence an. Here it is. This is L. And then the main, this is easy. The conversion is instant. It's something trivial to do on a computer. And then the important and costly part is this one, minimization. And so that was, well, considered in theory by Adam Chesky and Rival, and last year solved in an efficient way, let's say, with, and we also have an implementation on which the new transcendence test is also based. So this will compute here the least order LF min that annihilates F. In this case, it's precisely the same. It's just a monic version of this. So it's 1 over the leading coefficient times L. And then the last step is just look at local solutions. If you notice some, and this we know how to do, there are algorithms. There's a Frobenius method and algorithms, efficient algorithms, for instance, by the Chudnovsky brothers. Then you look at local solutions, you notice there are logs, and then you conclude F is transcendental because, once again, by the key property. Otherwise, F algebraic would imply a full basis of algebraic solutions for LF min. So no log, but this is incompatible with the presence of logs there. Okay, so let me just tell you that this, yeah, there is a general way to reduce deciding algebraicity via this new tool, minimization, or recent tool, minimization. So Stanley's problem is reduced to Fuchs's problem via minimization in this way. So that's the second algorithm for Stanley's problem. First, compute LF min instead of LAlg, and then decide if LF min has only algebraic solutions. This you can do in a theoretical way using Singer's algorithm from 79. So that's a complete algorithm. If LF min has only algebraic solutions, then you return that F is algebraic. If not, you return F is transcendental by the previous fact, basically. So once again, this second algorithm solves in theory Stanley's problem. That's the second proof that algebraicity is decidable, but there is a new drawback, is that step 2 can be very costly in practice, not because of the computational LF min, but because we need here in the second step to apply Singer's algorithm from 79 that relies on, among other things, on what I recalled before, factorization, solving Abel's problem, and computing huge, well, solving huge polynomial systems. So now the last thing is about the practical transcendence test, and that's the third, what I call the third algorithm for Stanley's problem. Once again, we start with this computation of LF min, and then, as in the upper case, if we notice that there is a logarithmic singularity in this LF min in the local solutions, then we return transcendental, otherwise we return A. Well, this is what I should call it a semi-algorithm, because it is always correct a priori only when it returns transcendence by the facts I recalled before. Now, the thing is that conjecturally, there is a conjecture, as I said at the beginning, due to Christol and André, saying that under the additional assumption that F is, in addition, globally bounded, then this algorithm is also correct when it returns A. So for instance, when F is at the diagonal of a rational function, as in some in my examples, then this algorithm should also be correct once this conjecture is proved. And if it's disproved one day, then it will be incomplete. It will only be correct if, when it returns T. And yeah, this is the the example that I mentioned of a difficult quadrant model with repeated steps. Remember, that was example C. And the proof is the following of the transcendence of this thing is, well, first, a step that is based on something that I didn't discuss today, the Gaussian proof. So by this technique, we first compute a differential operator L for F over the 11 and degree 73. And then here, steps 2, 3, and 4 actually are a very particular case of the minimization procedure. So that gives you an idea about how this works. So we first, by a study of possible apparent singularities, we deduce that if the order LF min is at most less than 11, then the degree is less than this number, and this can be ruled out, this possibility, by let's say, linear algebra or structured linear algebra, or in more fancy terms, differential Pade, Hermite-Pade approximants. So we deduced that actually the input was already minimal, but it has a logarithmic singularity at 0. So once again, FD should be transcendental because of this key fact. This is a computer-driven discovery and proof, no human proof yet of this result. This is the example I mentioned at the very beginning. All the other criteria and algorithms fail or do not terminate. For instance, the criteria do not apply because the asymptotics of these coefficients really are compatible with coefficients of algebraic functions. And one last thing is transcendental takes about 1 minute to prove transcendence. So it's quite fast. So I'm basically finished. So the takeaway message is that these 3 problems on algebraicity of solutions of LDEs are decidable. In practice, proving transcendence is easier than proving algebraicity. That's a funny fact, and well, it's not completely in accordance with what's happening on numbers, but that's life. And minimization, this famous minimization, and that I quoted several times, is a practical alternative for proving transcendence. It allows to solve difficult problems from applications. It's useful in other contexts. So in the paper with Bruno and Tanguy last year, we applied it to what's called effective Ziegel-Shvidlovsky theorem that decides algebraicity or transcendence of values of E functions. And I think that's all. Thank you very much for your attention. There are further things, but we can discuss if you have any questions. Thank you very much, and sorry for being a bit late.
Thanks. Thanks, everyone. So do we have any question for that?
Let me display the last thing, and maybe this will provide some inspiration for some of you.
I have a question. So all of this is over Q. Oh, first of all, thank you for the really nice talk. It's always a pleasure to hear you speak about your work. All of this is over Q. Is there anything quick that you can say about what if we try to do something like this over a number field?
Well, that's a good question. The short answer is that there should be, at least. So let me focus because there are many approaches. Concerning this fast approach based on minimization, in theory, minimization is also decidable over a number field. That was also proved by in this paper that I mentioned by Adamczewski and Rivoal. But that was so the stability question is solved. So from a purely theoretical perspective, the answer is yes. But then if we want to make it efficient, we need a different algorithm. And that's what we did with in that paper that I cited with Tanguy, Rivoal, and Bruno Salvi. And in that case, we only consider the case of not of a number field, but just of Q. So this remains to be done. It should be doable. But it's not solved yet. I mean, not in that. There is no efficient algorithm for that, for minimization for power series with the linear differential operators with coefficients in K of T or K is a number field.
Thank you.
So we have a question in the chat.
Yes, so it's about my slide on generating functions. So let me answer this. Yeah, so actually, maybe we look at this example that I couldn't comment anyway. So we have these allowed steps are these ones. So we can go this way, this way, this way. I mean, these 5 ways, but to the west, there are 2 ways of going to the west, the blue way and the red way. So for instance, if we want to understand this 8, this is about the number of walks in the quartal plane. So that should stay confined to the lattice and squared that use precisely 3 steps. And that anywhere on the axis. So it is uniquely defined because you cannot go, because these steps are short, are small. You cannot go too far using these steps. So in this precise case of length n is equal to 3, you see there are 8 ways of doing this. So you go east, east, west, and then you end on the axis. A second one is east, east, blue, west, and then you see the other possibilities. So for any, there is no issue with the, you can consider the number of walks that in precisely n steps and on the axis, horizontal or also vertical axis. If the answer is not clear enough, please let me know.
Question.
Go ahead, Petra.
Yes, I just wanted to know how the initial values are used in your algorithm. For instance, in the array sequence, I didn't get really how you use it to prove that it's certain that.
Yeah. Okay, so you see here, actually the algorithm starts, I mean, the one that so here we started with the binomial sum, but actually the minimization, the true algorithm starts, let's say, at after step 2. So this is the input of our algorithm. We have this, we have our array power series defined as a solution of this L with precisely these two initial conditions, right? And your question is how, where do these initial conditions play a role? And the answer is, well, they will play a role in the minimization. So for one, you can imagine that this operator has, okay, maybe not this one, but a similar one may have several power series solutions, and for some of them there exist shorter, smaller order annihilating equations. But for some of them, this one is already minimal. And this is where it's about, so it's a very, let me go even back. Maybe that was a bit too quick, but I think the answer is already there in this slide here. So for the same linear differential equation, this one in blue, if I swap these two initial conditions, well, the first one is transcendental, the second one is algebraic. And one reason for this is that for the first one, this is really the minimal for the log, actually. For the log, this is the minimal order differential equation. While for the second one, well, the second one in disguise is just a constant. Just the constant -1. And for this one, the minimal operator is partial, t. So in the minimization, if you give this data, the last one, the last row, to the minimization procedure, it will find that it is, well, just partial. While if you give these initial conditions, it will find that this is the minimal operator. So it plays, of course, it's not obvious in which way, because I didn't explain how the minimization procedure works, but that's the idea. Initial conditions play a fundamental role in the minimization already.
Right, so we have another question in the chat about incompatible asymptotics.
Yes, let me go back then. Yes, incompatible with what? Exactly. So that was a bit too quick. Here, so what I said is that algebraic power series have several types of properties: algebraic, arithmetic, analytic. Let's focus on these analytic properties. I said that if f is algebraic, then an, if it grows like this, kappa rho to the n to the alpha, then alpha, rho, and kappa are constrained by these conditions. That's a result of a theorem, a combination of theorems by due to Puiseux, Darboux, and Flageolet. So what I call incompatible is, for instance, if I have a sequence such that the corresponding row in the asymptotics is a transcendental number, then I know that this is not compatible with the algebraicity. So I can already conclude that this F is transcendental. Well, usually in the applications, this will always be satisfied most of the time. But so alpha, if alpha is a negative integer, then we know that F is not algebraic. But it could be that there are transcendental power series with alpha that is rational, non-negative, and integer non-negative. So in that sense, this alpha is compatible with algebraicity. So we cannot simply, in such a case, and that was the case with my lattice path with the colored wests. In that case, I said that alpha, the corresponding alpha that I didn't display, actually belongs to this set. So even if we manage to prove that this alpha is exactly that number, we cannot conclude directly that this power series is transcendental because it could well be algebraic with this in this set. Is this clearer now? Right.
So may I ask, I mean, these algorithms work for any D-finite power series, right?
With coefficients in Q.
With coefficients in Q, right. So how sensitive is the concept of D-finite to, well, certainly, I mean, if I change a initial segment of the power series coefficient, I suppose it remains D-finite, and it has this nice asymptotic property as well, right? I'm assuming, right, that it will have.
Well, so being D-finite only depends on the differential equations, so and not on the initial conditions, right. And also being satisfying a linear recurrence with polynomial coefficients, so being p-finite on the level of the sequence, that only depends on this recurrence operator, not on the initial conditions. That's correct. But then, for the same operator, the differential operator, or equivalently for the same recurrence operator, and different sets of initial conditions, the asymptotics may change dramatically. In some, yeah.
So you're saying that the asymptotic properties may vary with the initial conditions?
Yeah, for instance, the same example, the example of the log of 1 minus t. You remember this one is solution of a second order differential operator,
right,
that has a constant, that has no constant term. So that means that as soon as you have log of 1 minus t in your solution space, you also have the constant 1. And of course, the asymptotics in the expansion of this power series, trivial power series 1, is very different from the one of the coefficients of the log that have this alpha is equal to minus 1, right? Minus 1 is in Q minus Z negative. So it's incompatible. Once you have 1 over n in the coefficients, you know that your power series cannot be algebraic. But with the same differential equation, but different initial values, this alpha is equal to minus 1 changed suddenly to alpha is equal to 0 because it's just constant.
Okay.
So it's sensitive to initial conditions. That's yeah.
So
hence, also the property of being. So hence the property of being algebraic or transcendental depends very heavily on the initial conditions.
Right.
Also integrality depends. So this is something that I mentioned very briefly. That I had an example, actually any example coming from combinatorics, where you know in advance that your sequence counts things. So it has, you know in advance that by design it has integer coefficients. But then when you write down your linear recurrence with polynomial coefficients, we look at this recurrence, there is no reason why these numbers should be integer. It's really a miracle provoked by the initial conditions. And by the way, for most of the time, if you change even slightly the initial conditions, everything will change in the sense that these sequence will not be integer anymore, not even almost integer, not globally bounded anymore. These things are related.
All right. So unfortunately, we've run out of time for today's meeting. So let us thank Alin again for a great talk. Thanks so much.
Thank you very much. Thank you for the invitation and for attending. Thank you.
Alin, could I ask a really quick question before you leave?